So what we're going to look at is we're going to look at this one baby's stool, the fecal community, which represents the gut, sampled every week for almost 2.5 years. And so we're starting on day 1. What's going to happen is that the infant is going to start off as this yellow dot, and you can see that he's starting off basically in the vaginal community, as we would expect from his delivery mode. And what's going to happen over these 2.5 years is he's going to travel all the way down to resemble the adult fecal community from healthy volunteers down at the bottom. So I'm just going to start this going, and we'll see how that happens. What you can see, remember each step in this is just 1 week. What you can see is that week to week, the change in the microbial community of the feces of this one child, the differences week to week are much greater than the differences between individual healthy adults in the Human Microbiome Project cohort, which are those brown dots down at the bottom. And you can see he's starting to approach the adult fecal community. This is up to about 2 years. But something amazing is about to happen here. So he's getting antibiotics for an ear infection. What you can see is this huge change in the community, followed by relatively rapid recovery. I'll just rewind that for you. And what we can see is that just over these few weeks, we have a much more radical change, a setback of many months of normal development, followed by a relatively rapid recovery. And by the time he reaches day 838, which is the end of this video, you can see that he's essentially reached the healthy adult stool community, despite that antibiotic intervention. So this is really interesting because it raises fundamental questions about what happens when we intervene at different ages in a child's life, right? So does what we do early on, where the microbiome is changing so rapidly, actually matter? Or is it like throwing a stone into a stormy sea, where the ripples will just be lost? Well, fascinatingly, it turns out that if you give children antibiotics in the first 6 months of life, they're more likely to become obese later on than if they don't get antibiotics then, or only get them later. And so what we do early on may have profound impacts on the gut microbial community and on later health that we're only beginning to understand. And so this is fascinating because one day, in addition to the effects that antibiotics have on antibiotic-resistant bacteria, which are very important, they may also be degrading our gut microbial ecosystems. And so one day we may come to regard antibiotics with the same horror that we currently reserve for those metal tools that the Egyptians used to use to mush up the brains before they drained them out for embalming. So I mentioned that microbes have all these important functions, and they've also now, just over the past few years, been connected to a whole range of different diseases, including inflammatory bowel disease, heart disease, colon cancer, and even obesity. Obesity has a really large effect, as it turns out, and today we can tell whether you're lean or obese with 90% accuracy by looking at the microbes in your gut. Now, although that might sound impressive, in some ways it's a little bit problematic as a medical test, right? Because you can probably tell which of these people is obese without knowing anything about their gut microbes. But it turns out that even if we sequenced their complete genomes and had all their human DNA, we could only predict which one was obese with about 60% accuracy. So that's amazing, right? What it means is that the 3 pounds of microbes that you carry around with you may be more important for some health conditions than every single gene in your genome. And then in mice, we can do a lot more. So in mice, microbes have been linked to all kinds of additional conditions, including things like models of multiple sclerosis, depression, autism, and again, obesity. But how can we tell whether these microbial differences that correlate with disease are cause or effect? Well, one thing we can do is we can raise the mice without any microbes of their own in a germ-free bubble. Then we can add in some microbes that we think are important and see what happens. When we take the microbes from an obese mouse and transplant them into a genetically normal mouse that's been raised in a bubble with no microbes of its own, it becomes fatter than if it got them from a regular mouse. Why this happens is absolutely amazing, though. Sometimes what's going on is that the microbes are helping them digest food more efficiently from the same diet, so they're taking more energy from their food. But other times, the microbes are actually affecting their behavior. What they're doing is they're eating more than a normal mouse, so they only get fat if we let them eat as much as they want. So this is really remarkable, right? The implication is that microbes can affect mammalian behavior. So you might be wondering whether we can also do this sort of thing across species. And it turns out that if you take microbes from an obese person and transplant them into mice that you've raised germ-free, those mice will also become fatter than if they receive the microbes from a lean person. But we can design a microbial community that we inoculate them with that prevents them from gaining this weight. We can also do this for malnutrition. So in a project funded by the Gates Foundation, what we're looking at is children in Malawi who have kwashiorkor, a profound form of malnutrition. And mice that get the kwash community transplanted into them lose 30% of their body mass in just 3 weeks. But we can restore their health by using the same peanut butter-based supplement that's used for the children in the clinic. And the mice that receive the community from the healthy, identical twins of the kwash children do fine. This is truly amazing because it suggests that we can pilot therapies by trying them out in a whole bunch of different mice with individual people's gut communities, and perhaps tailor those therapies all the way down to the individual level. So I think it's really important that everyone has a chance to participate in this discovery. So a couple of years ago, we started this project called American Gut, which allows you to claim a place for yourself on this microbial map. This is now the largest crowdfunded science project that we know of. Over 8,000 people have signed up at this point. What happens is that they send in their samples, we sequence the DNA of their microbes, and then we release the results back to them. We also release them de-identified to scientists, to educators, to interested members of the general public, and so forth, so that anyone can have access to the data. On the other hand, when we do tours of our lab at the Biofrontiers Institute, and we explain that we use robots and lasers to look at poop, it turns out that not everyone wants to know. But I'm guessing that many of you do, and so I brought some kits here if you're interested in trying this out for yourself. So why might we want to do this? Well, it turns out that microbes are not just important for finding out where we are in terms of our health, but they can actually cure disease. This is one of the newest things we've been able to visualize with colleagues at the University of Minnesota. So here's that map of the human microbiome again. And what we're looking at now, I'm going to add in the community of some people with C. diff. So this is a terrible form of diarrhea where you have to go up to 20 times a day. And these people have failed antibiotic therapy for 2 years before they're eligible for this trial. So what would happen if we transplanted some of the stool from a healthy donor, that star down at the bottom, into these patients? Would the good microbes do battle with the bad microbes and help to restore their health? So let's watch exactly what happens there. 4 of those patients are about to get a transplant from that healthy donor at the bottom. And what you can see is that immediately you have this radical change in the gut community. So one day after you do that transplant, all the symptoms clear up, the diarrhea vanishes, and they're essentially healthy again, coming to resemble the donor's community. And they stay there. So we're just at the beginning of this discovery. We're just finding out that microbes have implications for all these different kinds of diseases, ranging from inflammatory bowel disease to obesity, and perhaps even autism and depression. What we need to do, though, is we need to develop a kind of microbial GPS where we not just know where we are currently, but also where we want to go and what we need to do in order to get there. And we need to be able to make this simple enough that even a child can use it. Thank you.